So this is the short version, right? So if some object in a frame of reference is moving with respect to us, we will see their clock run slower. Now, by the way, when they look at our clocks, they see our clocks running slower. It's all relative, right? But as this car speeds past us, we'll see its clock tick slower. Okay, the length of the car is going to contract. The mass of the car is going to increase. Okay, now at 0.866, the speed of light. Okay, it turns out that the Lorentz factor, the factor by which all of these things change, the Lorentz factor is 2. Okay, and the Lorentz factor is this little thing that's 1 over square root of 1 minus v squared over c squared. Okay, if you do that with 0.866, you get a factor of 2. Let me just show you this. Okay, so the Lorentz factor is 1 over square root of 1 minus, and then it's 0.866 c squared over c squared. Well, you see that the c squareds are going to go away. And so you end up with 1 divided by the square root of 1 minus 0.866 squared. And that's 1.99982 or something like that, right? Okay, so that's approximately 2, okay? So as this car moves to the left past us, we see its frame of reference contract, but only in the direction that it's traveling. So it's like, when you take an auto shape or something like that and click on it, you just drag the side that's parallel to the velocity in. Okay, this makes the clock not round, the wheels of the car not round, and they really are not round, okay? Okay, so the car shrinks in the direction it's traveling from 6 meters to 3 meters. The mass increases, right? And you're saying, where does that mass, where is it coming from? Well, the answer is the mass comes from the kinetic energy, right? It's got so much energy at 0.866, the speed of light, that it's doubled its mass, right? Half of its mass is kinetic energy, half of it is rest mass. It's crazy, right? And the second hand, as it goes by us, takes 2 seconds for it to tick. We watch it, it's like, well, that thing's slowing way down. Okay, so let's take a look at the quandary here, right? 26 centimeter diameter clock. So the clock on that car, maybe, right, has a mass of 2 kilograms. It travels horizontally past us at 0.9 the speed of light. How does the shape of the clock change? Well, what's going to happen here is that it's going to go from round to oval. Okay, the height isn't going to change. This is going to be 26 centimeters, but the width of this is going to change, right? So our length is going to be the original length times the square root of 1 minus v squared over c squared. Okay, so that's going to be 26 centimeters times the square root of 1 minus, and again, 0.90 c squared divided by c squared, right? Let's do this. Okay, so let's see, 26 times the square root of 1 minus, and I just have to go 1 minus 0.9 squared. That's why you always use the factor of the speed of light, right? Okay, because it's so convenient. Okay, so this is 11.3. So it's 11.3 wide, 11.3 centimeters wide, 26 centimeters tall. What is the mass of the clock as we observe it? Well, the mass increases, right? So length contracts. Length contracts, mass dilates, which means to get bigger. Okay. And the mass, so the mass is going to be its rest mass divided by that. Right, so it's going to be 2 kilograms divided by this thing that's going to get less than. Right, so it's going to be 2 divided by the square root of 1 minus 0.9 squared. And I get 4.588. Right, which means, by the way, its rest mass is 2 kilograms, right? So that means that it has 2.588 kilograms of kinetic energy. What does that mean? What exactly does that mean? Well, that means that if E equals mc squared, right, the kinetic energy of this thing is that 2.588, right? That's how simple kinetic energy is, right? Kilograms times c squared, right? That's tremendous, right? C squared, c is 3 times 10 to the 8th, right? So c squared is 9 times 10 to the 16th, right? It's a huge amount of energy, right? Okay. All right. How much time in our frame of reference does it take the clock to register 100 seconds? Well, it's going to take longer. The clock is ticking slower, right? So it's going to take more than 100 seconds. So we're saying we look at that clock as it goes by, it's ticking slower. And how much time in our frame of reference does it take the clock to register 100 seconds, right? So that's going to be t, time dilates, right? So it takes longer, right? So t is equal to the, over the square root of 1 minus e squared over c squared, okay? So that's going to be, it's 100 seconds divided by the square root of 1 minus 0.9 c squared over c squared. Okay, so 100 divided by the square root of 1 minus 0.9 squared is 229 seconds. Right, now you can, the time is going to actually dilate by the same factor as the mass dilates, right? And it's also the same factor by which the length contracts, right? Now, here's a final way to ask this question, right? If we see the clock for 1 second, how much time does the clock tick through? Well, since the clock is ticking slower, it's going to be less than 1 second. So I'm going to go 1 second times this factor. Gotta have that thing longer like that. Okay, because I want to make a number less than 1. Don't try to worry about like, oh, what's the proper time or whatever, right? Just think about it. If the clock is ticking slower, it's going to be less time. So the time that we see, I'll just put that in quotes, right, is going to be less than that. And then to get less, you multiply by that factor. So 1 times the square root of 1 minus 0.9 squared is point. So it's going to tick through. Our clock, it's running at a normal speed, right? It's going to tick through 1 second. That clock will tick through 0.43588 seconds. Okay.